I have no idea if this is going to work. If I did my job right, though, it should be a Type A difiler file now. Hello, Internet. My name is Quinn, and this is Blondihacks. This is the final episode of the MLA18 difiler project. That's right. Today we are going to seal it up, we're going to paint it, we're going to make difiler files. That's going to be really cool, and we're going to make first chips on this machine. So let's go. First order of business is to tear it down so we can get ready for final assembly. We've got all the parts made, so we should be able to put it together for hopefully the final time. I'll get the table off here and get the rest of the pieces broken down here to get ready for the next final steps, which is going to be securing the bearings in place. All of the bearings on this machine are held in place with Loctite. Most of them will be easy. The crankshaft bearing, though, is going to be tricky. All the clearances in the Scotch yoke crank mechanism inside the machine are all determined by the lateral position of the crankshaft bearing in the casting. That was easy to get right when the machine is in this stage because you can just tap the bearing back and forth as needed until everything runs smoothly. However, on final assembly, everything's going to have to get Loctited in place, and that Loctite is going to cure as soon as the bearing is in place and there's no more air inside there. So there isn't going to be an opportunity to slide it back and forth and adjust it and then secure it in place. We're going to have to kind of get it in one. And that's the part I'm most concerned about here on assembly. You can see how long that crankshaft bearing is, so it's very secure once it's in there with Loctite. In preparation for said Loctite, I'm going to clean out all the bores with acetone, make sure everything's clean, dry, degreased, etc. The bond of Loctite depends very much on surface prep, but if everything is clean and properly prepped, then Loctite 603 is actually stronger than a mild interference fit. There's actually data on that on their website. It's pretty interesting. I mean, you know, it's coming from them, so maybe it's exaggerated, but Loctite is very, very strong. All these bearings have a position that they need to be in, and it's a little bit of a race against the clock to get the position set before the Loctite starts to cure. As soon as the bearing is in place and the Loctite experiences an anaerobic environment, it starts to cure very quickly. This lower file rod bushing's position is set by the plug there at the bottom, so I had to get the plug in quickly after the bushing was set, and then turn it upside down so everything's sitting in the right place when the Loctite cures. The upper bushing is a little bit easier because it just needs to sit flush with the top surface of the casting. So I feed that down and just hold it for a minute there in that position, and the Loctite will cure sufficiently to hold it in place and then wipe off the excess. Those two bushings need to be in perfect alignment, so while the Loctite cures, I'm going to put the file rod in place just to hold everything in position. In principle, this shouldn't be necessary because everything's machined to very close tolerances there, but just in case, make sure nothing moves and that the file rod is going to continue to move freely up and down. While I wait for that, I will finish the bright steel parts. For this, I'm using Shield T9. This is really good stuff. It's not cheap, but a very little bit of it goes a very long way. This tiny can here has lasted me almost 10 years. You just need a little bit of a spritz. Honestly, about half as much as I used there would have been fine. You just rub it all around the parts, and then you let them sit, and the solvent in there flashes off, and it leaves basically what's a very thin coating of wax on the parts. It's really effective. I've never had a part treated with this stuff rust. I also used the residue of Shield that was still on my gloves there to treat the edge of the table. Now for the top of the table, though, I'm going to do something different. Shield's one disadvantage, being a wax-based product, is that the finish that results is not perfectly slick and smooth the way that an oil is. So for the top surface of the table, which I do want to be very slippery, I'm going to use whey oil. Just rub that into the surface and wipe off the excess. This will also prevent corrosion with 100% effectiveness, but with an oil on cast iron, you do have to replenish it maybe once a year or so. You need to reapply it. Okay, now for the hard part, the crankshaft bearing. Like I said at the top, this has to be in just the right position. My plan for this was to apply the Loctite to the bearing, slide it in there, and then very quickly get the rest of the mechanism assembled before the Loctite had fully cured, and then I can adjust the position of that bushing a little bit as needed. This turned out to be a terrible plan that did not work at all, so stay tuned. I fed the bearing in until it was flush with the end of the casting, which I knew was going to be very close to the correct position, but probably not exactly right. And then I did my best to hustle up and get the rest of the mechanism in there. I cover everything with some startup oil just to make sure that it's going to be well lubricated when the machine first runs on all the surfaces that are going to be rubbing against each other. Looking back on this approach, I don't know what I was thinking. It's painfully obvious watching this video that the Loctite has already started to set as I'm frantically getting all these little pieces installed. And this is the moment where I realized I was in trouble when I tried to slide the file rod in and it wouldn't even go into the yoke because they weren't sufficiently well aligned. The crankshaft web is too far towards the camera in this perspective, which means that the crankshaft bushing is pushed too far in, and thus the crank web can't be pushed back far enough to allow the yoke to align. So I tried to then move things by pushing the crankshaft bearing back a little bit, but the glue was too set at this point. The Loctite had done its thing, and that crankshaft bushing was not going to move. I considered my options at this point. I could have heated up the Loctite to break it free and try again, but I decided the easiest thing to do, because it was close, was just to lap the face of the yoke down a little bit to move the hole back a little bit, effectively make the yoke thinner so that the holes would align again. After a few minutes of that lapping, I did a test fit to see how I'm doing and see if I'm even in the ballpark of this idea working. And I could tell that it is actually working. So the file rod now goes into the top of the yoke, but it won't go all the way through, and the mechanism won't move. So alignment is improving, but it's got a long ways to go, it turns out. So I learned that I'm on the right track, but I'm going to need to get a little more serious about material removal. Lapping is fine if you're within a few tenths of what you need, but I'm within a few thousandths of what I need, so it's time for the files. Got a nice smooth file here, and I've covered the slide block with Sharpie so I can make sure I'm filing that even and flat, not changing the shape of the part or creating tapers or anything. I worked the slide block and the yoke down a little bit at a time until I'd removed probably a few thousandths off of each, and then I did another test fit. I'm glossing over this process here in the interest of not boring you to death. There was actually quite a bit of back and forth between filing a little bit and test fitting, but I did eventually get there. The file rod now slides in nicely, and the mechanism is running smoothly once again. This little fit and finishing phase of a project like this is something that always gets glossed over in kits and project write-ups. In hindsight, I think a better design here would have been to hold the crank bearing in place with a couple of set screws, because then you could adjust it laterally a little bit. That would make a huge difference in how easy this machine is to get up and running and get it to run smoothly and quietly. Having everything depend so crucially on that lateral position of the bearing that's quite difficult to get right is not the best part of this design. Okay, let's talk about files. Die filers use two different types of files, types A and B. Type A files cut on the downstroke and type B cut on the upstroke. You know which your machine is because if it's a type B, then it'll have a foot that holds the piece down against the table, because of course the upstroke cutting file is going to tend to lift the piece off the table. This file is a type A die filer. However, type A die filer files are virtually unobtainium nowadays. You can still find them, but they are very, very expensive, like hundreds of dollars expensive. Hey folks, Editor Quinn breaking in here. Since this was recorded, my patrons actually let me know that there is at least one more company that is still selling these files at a reasonable price, and that is Falcon Tool Company. They say on their website that they have a large leftover inventory of these files that they are selling off, and as of this recording, they are really quite cheap, 15 bucks a piece. But when they're gone, they're gone. So I went and picked up a whole bunch of these, as you can see, different aggressivenesses and different shapes and so on. If you have a Type A die filer, I recommend heading over to Falcon Tool Company and get them while you can, because when they're gone, they're gone. That said, learning how to make these is still a super useful exercise, because of course these files will be gone someday, so let's go through that now. The kit comes with instructions for making die filer files out of hand files. Now, of course, Type A again cuts on the downstroke, and hand files all cut the other way. They cut on what would be the upstroke, because of course hand files are intended to be used like this, where you're cutting on your push stroke. So what we need to do then is flip these files around and find a way to mount them thusly in the machine. Now there's an additional wrinkle here, which is that die filer files have to be what are called pillar files or parallel sided files. And hand files these days are all tapered for the most part. So this taper is no good. We can't have any of that in the file because that won't work properly. Some pillar hand files do still exist. This is a chainsaw file, and these are still parallel-sided files for some reason. These are one of the few applications where parallel files live on. So the other thing we can do is take a tapered file like this and there's generally a straight section at the base of it, and we can just cut that section out and use that, ignoring the tapered section at the end. So if we can get this section out and then flip it around and put a tang on the other end for use in the die filer, then we will have a type A die filer file that works correctly. That's the game here. Step 1 is to figure out how much of the parallel section or pillar section of the file we have. I want to get as much length on this file as I can because it's going to be close to being long enough at all for what we need to do. I'm checking to see where the taper begins on this particular file. They all vary a little bit in this regard. As soon as I see the taper start, then I know I need to cut short of that. Next, I double check that I'm going to have enough length here. The overall length of these files has to be about 3¼ inches. So it looks like I will have just barely enough of that. The tang that we're going to make can be in the tapered section. That's fine. I just have to have parallel or pillar file section above the table for this machine to work correctly. Because files are very, very hard, you can't cut them with any sort of toothed cutting tool. So I'm going to snap it instead. I put a little nick in it with a Dremel, and I'm just going to hit it with a hammer until it snaps off. Or at least you're supposed to be able to do this, but fun fact, the heel end of this file is actually not as hard as the other end of the file is. That's pretty typical for hand tools. You'll see this on screwdrivers, drills, other similar tools. The shank is usually a little softer because that way it won't break when you're pushing on that end. But I did manage to get that to break after working it back and forth a little bit. Got a pretty clean break there, and I'll do the same at the other end. This end of the file is extremely hard, and so this should shatter very easily. And boy, did it ever. The next step is to prepare a mandrel that will go on the file. I've got a piece of scrap that I'm going to use for this. It's rather oversized, but the size doesn't matter. We're going to be turning it down. I'm going to start by putting a hole in it, which is not very on center because I didn't center drill it first, but again, that won't matter for this operation, as you'll see. The order of operations to ensure concentricity on the final file is actually pretty clever. Again, that comes straight from the instructions in the kit. This is not my invention. The next job is to put a new tang on what's basically the wrong end of the file. You have to do this on some sort of grinding tool, of course, because files are once again extremely hard, much harder than any of your lathe turning tools. Now I'm choosing to do this on my bench grinder, and I've fit the file into my hand drill there. Even though the file is square, the hand drill actually holds it reasonably concentric, sufficiently for this anyway. Again, the cleverness of this order of operations is that we don't have to achieve really good concentricity with any of these low precision methods. Just get any kind of round-ish tang on there that's concentric-ish, and this will all work out in the end, as you'll see. I go back and forth a couple times to the lathe and the bench grinder test fitting until that file is a good fit in that hole that we drilled. The diameter of this is not super critical, it just needs to be a reasonably close fit in the hole on the lathe. My new tang is a really good fit, so I think I'm ready to move on to the next step. I can now part off this proto-mandrel, if you will, or proto-tang, I guess, on the file to a reasonable length, something that matches the file tang that I ground onto the file, because we're going to be turning this mandrel down in a minute. And a Yahtzee. Before I can do that, I need to join these two together for life, and for that, it's time to bust out the JB Weld. I'm going to clean everything up, degrease it thoroughly here first with isopropyl alcohol. Make sure that the glue surface is going to have a really good bond. Much like Loctite, JB Weld is extremely strong if you do proper surface prep and allow proper curing and have proper clearances and so on for it. People who don't have faith in things like modern epoxies usually haven't done their prep work properly, but they are really incredibly, incredibly strong. It also helps to make sure you use the best versions of each of these products. In the case of epoxies, they often come in 5-minute versions and 24-hour versions. Always get the 24-hour versions. The faster a glue product cures, the less strong it is. So you want the good stuff, get the slow curing stuff. Yeah, you have to wait a day, but it's worth it. With everything good and globbed up with JB Weld, I cleaned off the excess, and then I leave that sit for, again, a full 24 hours before I touch anything. We really can't do the next steps until that JB Weld is at full strength. While I wait, I can prepare the other file, the round file. If you can find genuine pillar files like this, the process is a lot easier because you can cut it anywhere you need to, and if the file is long enough, sometimes you can actually get 2 die filer files out of a single hand file. Finding genuine pillar files, though, is very difficult. This round file, which again I believe is a chainsaw file, is the only one I was able to find. Otherwise, the steps are all the same, but of course with a round file, everything's a little bit easier because of course you can hold round files and drills and things much easier. Now comes the really clever bit of these instructions. You chuck up the file in your lathe. This is again with the JB Weld fully cured, so it's good and strong. And I've got shim stock there to protect the file. Well, honestly, to protect the jaws and the file from each other. Probably the jaws would be more damaged by the file than vice versa. And we dial in the file so that the file is concentric. That's a little bit tricky, this being a small dimension square part. But if you're interested in how to dial in square parts, I do have a video on that in my Lathe Skills playlist, so go ahead and check that out. I've left just enough of the file sticking out here so that I can sneak in with the indicator and get that square profile dialed in. This doesn't have to be perfect, it just has to be close enough so that the final file will run reasonably well centered in the table. If the mandrel is running out at this stage, it doesn't matter because we're going to be turning it down to get it concentric with the file. So you see that's the cleverness here. We leave the mandrel oversized during all of the other phases, and now when we get to here, by turning down the mandrel, we're canceling out any error that's in the grinding that we did, or the drilling that we did in the mandrel, etc. All those errors magically go away because we're turning the mandrel down to be concentric with the file. I did this all with light cuts because the setup is not particularly rigid. It's being held by a small file, so there was some deflection here. But light cuts and some spring passes got it done. I'm aiming for a really close fit on the file holding system in this machine, which is that little hat and the hole in the end of the drill rod, as you may recall. I ended up a few tenths over nominal size, and I actually want to be a few tenths under so that there's just enough room to slide that file into the fixture. Rather than risking another cut, I'll just finish up with emery paper. That'll also have the nice benefit of giving me a really good finish on the part. That will also help slide it into the machine nicely, and it'll help keep it from rusting. Finally, a chamfer will ease insertion into the machine and, of course, separate us from the animals. Final check here to make sure I'm on the dimension that I wanted and that I've got no taper. I can fish that out of there now, get the aluminum shim off of there, and there it is, one die filer file, at least I hope. I have no idea if this is going to work. If I did my job right, though, it should be a Type A die filer file now. At this point, I still wasn't 100% sure how this file mounting system is supposed to work. It seems like the file slides into the end of the half circle on the drill rod there, but then the hat is supposed to go over top and hold everything in place. However, it's not totally clear to me how the hat is supposed to hold all of this together. It seems like it just goes on over top like that, and the set screw on the side squeezes everything together. I'm not sure if the set screw is supposed to go against the file or against the file rod half circle on the other side. The instructions don't explain this at all, and the drawings are not shown in a way that allows you to see which way this is all supposed to go together. I'm kind of guessing here. I put the set screw on the side touching the file, sort of pressing the file up against the half circle of the file rod. I hope that's right. Now I'll square up the table, make sure that whatever we file is going to be square. The table is easily adjustable both laterally for position and for angle. Well, I should be ready. Let's do some die filing. First chips on this machine. Very exciting. Still runs well, that's encouraging. Got a piece of brass square bar here, and well, it's doing something. What I'm learning very quickly here is that there is a technique to using this machine. There's definitely a learning curve. You have to get the pressure just right. The secret seems to be very, very light pressure. If you use too much pressure, the file will chatter. So it's sort of like using a rotary tool where you got to let the speed of the machine do the work, not pressure. So not like hand filing where you often use quite a bit of pressure. Here the pressure is very, very light. It seems to work best if you're just basically touching the part to the file. I've also learned that set screw on the hat has to be very tight or the file can pop loose, as happened here. And this was quite annoying because of course it damages the hole in the center of the table when that happens. I gotta say, I don't love the file retention system in this design. I feel like it really should have some kind of collet or something that really grips the file strongly. One little set screw I don't think is doing the job, but if you get it tight enough, it does work. So that was just me not installing it quite correctly. Let's try some sheet metal next. In principle, this should go much quicker because there's much less profile of material exposed to the file. And sure enough, this really chews up the sheet metal very, very quickly. You could definitely use this to hog through some material on sheet metal. It is noisy though, of course, because the material can flex a lot more than something thicker does. But that does a very, very nice job, I have to say. On the thicker stock, it works, but it is pretty slow. It's not going to remove material in a hurry. This is really more of a finishing tool. I'll try the round file next. This is a 3/16 round file. The square file was 1/4, so this is a little bit smaller. In with the same brass square bar once again. The round file works very well. It actually cuts quite a bit quicker. Both these files are zero cut, the coarsest form of needle files, so they should both be a coarse file. However, the round profile, I'm sure, means much more concentrated tool pressure, so it's able to cut much quicker. I don't know if there's a difference in file pattern. One of these files is American cut and one of them is Swiss cut, so perhaps the Swiss cut, which is the round file, is also a better tooth pattern for a die filer. I'm not sure. There's definitely going to be a learning curve on these files. I see now the need for the top cap and the hat on this machine. These filings really get everywhere. The whole top half of the machine gets absolutely covered in them. Okay, let's make this thing look nice. I've got some acid etch primer here from Restoration Shop and my go-to Pour 15 engine enamel paint. This is my MG Maroon or Burgundy that I like very much. I've used it on all my steam engines, and I'm going to use it here because I have a bunch of it that I have to use up. I start by prepping the surface with IPA as usual. You'll note that I'm painting the machine fully assembled. It might be slightly easier to disassemble the pieces first, but the oil bath is full in there and I don't want to deal with draining the oil and having to make new gaskets and everything. I'm showing you the events slightly out of order here between this video and the previous one. There was no oil in the machine at the start of this video, but when I did that first chips demo, there was oil in it. So in between there, I cut some of that footage out, used it for the previous video, but in this video, the 7580 gear oil that I put in there is in fact in place as we record this. So I hope that all makes sense. Rest assured, I did not run it without oil in it for that first chips demo, but there is oil in it now. I am, of course, wearing a respirator. This acid etch primer especially is really, really toxic, nasty stuff. It's extremely effective, but plan ahead a little bit because whatever room you do this in will be uninhabitable for at least a full day after you apply this stuff. I'm doing this in a well-ventilated space and again with a respirator. I'm not bothering to mask off any surfaces here. I've done this enough that I can manage to not get paint on the machined areas. This Pour 15 paint is pretty amazing stuff. Hashtag not sponsored, but a little bit goes a very long way. I've painted multiple steam engines and now this die filer with it, and that little can is still 90% full, as you can see. This paint goes on in one coat. It goes on quite thick, and it's very durable. It takes a full week to cure. Being an enamel, I believe you can bake it to speed up the curing process, and in fact, it is an engine paint, so the idea is that the heat of the engine will bake the paint on, but it also cures if you just let it sit for a week, and I don't want to put this in my oven and fill my oven with nasty fumes. If you have a shop oven like some folks do, this would be an option as well, but you can just let it sit. That's also fine. It's dry to the touch in a couple of days, and then you can handle it, and then just don't abuse it for the first week until the paint is fully cured. Reassembly is, of course, reverse of disassembly, as we say in cars, although it's actually true in this case. There is the final machine. It still works after being painted. That's encouraging. I do plan to build a stand for this machine. This board it's sitting on is temporary. There will be a stand that has the motor mounted underneath out of the way of the filings, and of course there will be a belt guard on it and so on. But for now I can use it thusly on the bench as needed and just stash it under a bench or something until I get around to building the stand for it. Since that first test, I've had some more practice and I've gotten a lot better at using the large square file. Got a really nice finish on that filed surface there. It's going to take some time for me to learn how and where is best to use this machine, the role that it's going to play in my workflows. It would definitely have been the perfect machine to use for making the foundation ring for my A3 locomotive boiler, as many of you joked. But I'm calling it. This machine is done. I'm pretty darn pleased with it. We'll see how useful it ends up being. The long-term test will be the real jury there, but it was a lot of fun to build. I learned a lot. There's a lot of tricky castings, so this was definitely an education for me to build this thing. Whether or not I use it a whole lot, I enjoyed the process either way. Well, thank you very much for watching, and thanks to my patrons who make all of this content possible, and I will see you next time.